Well, thank you very much for having me here. I've been on a number of panels, and I see Tim and Cherrick often, and I think this is the first time we can actually talk about all of our systems publicly at the same time. So I think that's good news. So what I'd like to talk to you about today is our efforts at NERSC to prepare our user community for the Cori architecture that's going to be coming online at NERSC in 2016. So if you don't know about NERSC, we are the mission computing facility for the Department of Energy Office of Science. So what this means is if your research project is relevant to the mission of the DOE Office of Science, and you need large-scale computing, you can likely get an account on our NERSC systems. And NERSC, I think when people think of NERSC, they know we have a really broad workload. So we have about 6,000 different users of our facility now, and that are spread around in about 700 projects. What's interesting is the number of users going up every year increases more than the number of projects. And so we were kind of reflecting back on this, and I think we're seeing a little shift in how some more scientists are accessing the data that's run by scientists that actually submit the jobs to the system. So the number of users that are submitting and running jobs isn't increasing as quickly, but we see the number of users that are accessing or sharing the data from these simulations. So this is a snapshot of our Cori system. We call it a pre-exascale system, and one of the reasons why we're calling it a pre-exascale system is that some of the technologies in Cori we expect we will see on future exascale systems. And namely, we'll have a large number of slower processing cores with longer vector units, and we expect to see really deepening memory hierarchies, which is pretty exciting and will also be a challenge to our users. The system's named after Gertie Cori, who was the first American woman to receive a Nobel Prize in Science. So let's go through the configuration of the Cori system here. So we'll have over 9,300 Knights Landing compute nodes, and I'll talk more about the processor in the next slide. We're also going to be getting some Haswell nodes as well, but that's not going to be the focus of the discussion today. The interconnect is the Aries interconnect from Cray, and this is actually the same interconnect that we have on our Edison Ivy Bridge system today. We expect about 5 times more application performance over that current Edison system now. So the I/O capabilities are pretty exciting. We'll have the Lustre file system with 28 petabytes of disk capacity and 700 gigabytes of I/O bandwidth. But in addition, we're also going to be having what's called a burst buffer, or a layer of NVRAM that sits between the system memory and the disk that will be used to accelerate I/O performance. And that will have about 1.5 petabytes of capacity and 1.5 terabytes per second of I/O bandwidth. A big part of this system is getting applications ready to use it. So we have been working very closely with both Cray and Intel to get these applications ready. And the system is going to be installed into our new facility on the Berkeley Lab campus. If you've ever been to Berkeley Lab, you know we live on a steep hill, and our new building is basically on the side of that steep hill. So you should come visit us, because I think someone said on a clear view you have views of 5 bridges from the top of that building. So come visit us. We're not there yet, but we should be there within 6 months or so. So let's tell you a little bit more about the Knights Landing processor. This is what is public. This is what Intel allows us to share publicly with you. I think there's some Intel execs in the room, so maybe we can chat afterwards about some things I'd like to be able to say that I can't yet. Okay, so the key point in for this processor is it's a many-core architecture, right? And it's self-hosted. So it's not an accelerator, it's not a coprocessor like the current generation Knights Corner architecture. It's Knights Landing, self-hosted. And so we expect then users can use the same MPI and OpenMP programming model that they're using now on our Edison Ivy Bridge system. And we'll talk about some of the challenges with that. So we know there's going to be, or we can say that there's more than 60 cores per node on this chip, and that each core will have 4 hardware threads each. It's based on the Intel Silvermont architecture, although there's quite a few significant enhancements for HPC. So if there's 60 cores on this node, they have to be interconnected somehow. And what's revealed right now is that they'll be connected in a 2D mesh architecture on the chip. And that, you can imagine, right, you have 60 cores put together somehow in a mesh architecture. Some of them are going to be closer to some memory domains than others. So we know there's going to be multiple NUMA domains on this node. Let's see, there's 32 flops per clock. We'll support AVX 512. And then the key point I want to highlight here is there's also high bandwidth on-package memory. So this memory will be about 5 times faster than the DDR4 DRAM capabilities. And our instance will have 16 gigabytes of this on-package memory. Okay. So let's talk a little bit about the on-package memory now, because 16 gigabytes, but will be on-package, but then you'll have 96 in DRAM memory. So you have to figure out, as an application developer, how am I going to use those 2 levels of memory, and what should I put into that memory, and what should I not put into that memory. So here are the different modes that you can use for the on-package memory. First of all, the first thing you can do is ignore it altogether. You don't have to use it. And if you don't use it, it acts as kind of a 3rd level cache. So that is the cache model. And your application would need no changes in order to use it in this mode. The second mode highlighted here is called flat model. That's the model where an application developer can explicitly allocate memory into the on-package memory. Okay? And then there's a hybrid mode where you can do some combination of the first 2. So I think this is a real opportunity. This high bandwidth memory is going to have significantly higher bandwidth, and that can really help our applications, because most of our applications aren't limited by the flops, right? They're limited by how quickly they can move data in and out from memory. So we're looking forward to getting some early hardware to take a look at this. So I think in summary, to be able to run effectively on the Cori architecture, what's really changed for the users is what's happening on the node. So we expect that our users will be able to use MPI between nodes now, right? But they're going to really have to increase their thread parallelism on the node, okay? And then they're also going to need to be able to take advantage of those longer vector units and improve data locality, which means using that on-package memory, or somehow having better cache accesses. All right, so that's the architecture we're dealing with, and so now let's talk about our NERSC's challenge. So our challenge at NERSC is that we have a really very diverse workload. And so what I've shown here is a pie chart with a breakdown of all the applications in their time that they used on our system. And this is 2013. I should be getting the 2014 numbers soon. So we have thousands of users, hundreds of projects. So how are we going to prepare all of these application scientists to run effectively on this new architecture? So fortunately, I think we have a little help. One thing you can see is at least all these pie slices aren't equal, right? So we have a very concentrated workload, in that the top 10, about the top 10 codes take up 50% of our workload, and the top 25 you get over around to 2/3. So we think we can make pretty good headway if we're really targeting some of these these key applications that use a lot of time, not only at NERSC, but at other centers across the DOE complex as well. So anyway, now let me talk to you a little bit about the NESAP program. This is the NERSC Exascale Science Applications Program. And our strategy is really to target 20 application codes and work deeply with those teams and take the lessons learned from working with those applications team and share it with our very, very broad community. I mean, I think at NERSC we have no other choice. We can't work with every single application team, and so we have to put a lot of emphasis on teaching and training and webinars and having great documentation for our users so that they can learn the lessons from some of these code teams. So we had a call for proposals, and we looked at the different codes that applied to the NESAP program. In the interest of time, I'm just going to show you the answer here, and that is these are the 20 code teams that we've chosen to participate in NESAP. So what you can see is there is some overlap with the CAR program. I just actually saw them today as well, so I think there's an overlap of about 4 or 5, something like that. I think which will be good. We will stress, we'll force people to see if they can run on two different architectures. So we have applications that span all the 6 Office of Science offices here. And then when you put those application codes next to our pie chart, this is basically the same pie chart but now colored with green. You can see we're getting pretty good coverage in terms of some of the applications we'll be working with. Okay. So I thought now that I would walk through a little case study. We've been working at this for some time now, and so I thought I'd show you some results and how applications are actually running on this architecture. So I'm going to talk to you about Berkeley GW, which is a material science application code. And we're fortunate because one of the consultants on our app readiness team is a key code developer. So it was a really good code to start working with. And so I'm showing the work of Jack Deslip from NERSC, who deserves all the credit for this work. Okay, so you get the answer in one graph here. So what we wanted to do was, we don't have the Knights Landing architecture, right? We wish Intel had it right now, but they don't. And so we have a choice of what are we going to use as a proxy for this Knights Landing architecture. And what we chose to do was to use the Knights Corner architecture. That's the coprocessor, but you can actually ignore the host and run the Knights Corner architecture as if it's a standalone system, right? So that's what we're doing. We're going to run this Berkeley GW code on the Knights Corner coprocessor as if it is its own node. And we're only going to use one, okay? And so the Knights Corner architecture, it also has 60 cores per node, 4 hardware threads each, but it only has 8 gigabytes of memory. So you have to make sure you have an application that actually can fit into the Knights Corner card. Okay, so why don't we take a look and see what Jack got initially. So this is an original version of the code. And so we're having a little contest here, and the contest is, can the host beat the host, which is a Sandy Bridge architecture, can it beat the coprocessor? And so this is the first, this is the original implementation of Jack's code, and this is on the Sandy Bridge host node, and he's actually using 2 processors here. So you can say, well, why isn't there an orange line here? Why isn't there any number for the Xeon Phi, which is the KNC, the Knights Corner card? Why isn't there any bar there? Well, the reason is that you couldn't actually fit it into memory, okay? And the reason was this was an MPI-only application, this kernel. And when you're using MPI only and you want to use 60 cores, then there's some overhead associated with those MPI buffers, and you run out of memory. So right now, he can't even run on the Knight's Corner card. Okay, so then the next thing he does is he says, I am going to refactor my code such that I could put OpenMP into this code. So I'm going to have 3 loops, one loop for MPI, one loop for OpenMP, and one loop that can vectorize. So just doing that, he did nothing else except for just really refactor this code. He ran it again on the Sandy Bridge host and saw a big improvement in application performance. So that probably comes from, well, you can do vectorization on the Sandy Bridge, taking advantage of that, and better cache locality, just right off the bat. So this change, adding OpenMP, putting the code into a format such that OpenMP could be added, is what allowed Jack to be able to add OpenMP and get the code to run at all on the Knight's Corner card. And when he does that, initially, you see it's about 2 times slower than running on the host. And this is actually what we see fairly often from our user base. If they run kind of naively or just out of the box onto the Knight's Corner card, they're seeing a slowdown of 2 or 3 times performance. But then the last step here is to turn on vectorization, and you see this huge improvement. And right about now, the host, 2 Sandy Bridge and 1 KNC are running at about equal there. So, one takeaway is that in preparing for the Knight's Corner architecture, Jack actually improved the application performance on Sandy Bridge quite a bit, right? And I think that's something good that we've learned, and I know that there's been similar lessons learned from Oak Ridge and Argonne, is that sometimes the changes you make for one architecture, they can help you for other architectures as well. Okay, so I want to put up one little code snippet. I don't love it when people put up code snippets in presentations, but I think this one's kind of fun. So, one thing that Jack had in his code, you guys see what this is? Right, it's an if statement within his loop. And so he was attempting, right, to be really clever and say, if I don't need to do this work, just skip it and go to the top. Well, it turns out, right, this little if statement was completely breaking vectorization, right? And he was better off just doing the work, even if he didn't need the calculation. And so, going through your code and finding these places where, you've broken vectorization, the compiler is unable to do work, can give you a really big speed up for not a lot of work to do. You can get a real big bang for your buck by looking at your loops in this way. And in fact, we recently had a hackathon and had one of the Intel, an Intel representative come out, and we were able to speed up a number of codes by, one was 10%, one was 30%, one was 2x, just in a few hours in an afternoon. So I don't know if that says something about the state of the codes or that it's actually can be pretty easy to make some of these changes to the loops. But I thought that was kind of good news. We'll keep moving here. And so now Jack has this optimized code, right? He thinks it's highly optimized. And he's going to take it. We took it to what's called a dungeon session with Intel and Cray. And they went to the Portland site at Intel. And they worked on improving the code further. And so, I think this is a different kernel, but you can see this is scalability with the number of threads. And in blue is, Jack's original code. And he came out of the dungeon session 2 days later, and he had a much more scalable implementation of this particular kernel. And then over here on the right, you see, similar before and after shots of working with Intel and Cray at this dungeon session. And again, so the blue is Sandy Bridge, the orange is Ivy Bridge, and the green here is the Xeon Phi Knight's Corner card. You can see in all cases the optimizations that you make for this one particular, you're targeting Knights Landing, but you've actually improved the performance on all three of these architectures. But there was one mystery, and the mystery that was still open was this particular kernel was running faster on the Haswell processor than it was on Knight's Corner. And you might say, oh, there's a number of reasons why that could be. But in this case, vTune revealed that the application was memory bandwidth bound on Knight's Corner, but not on Haswell. And that's a little odd, because if you just look at the pure stream memory bandwidth numbers, Knight's Corner actually has a higher number. So what was actually going on here? And I think this is a lesson learned I'd like to take to the panel discussion and debate hopefully we'll have here is, in this particular kernel, in this particular loop index, they had a certain trip count, a certain loop level that they were executing to. The required cache size for reuse was 1536 kilobytes. And so you can see that KNC, the L2 is 256, on Haswell it was 256. But what's happening is, so you're spilling out of both the L2 on both of these architectures, but what Haswell had is the L3 cache here. And so in this architecture, or in this kernel, on the Haswell architecture, you could spill over to L3, whereas you were going to the main memory on Knight's Corner. And so the lesson learned on this was that the loss of L3 really on the KNC system means that data locality is even more important. And I think for Knight's Landing, we're going to have to look and really see how we can use that on-package memory as well. Okay, so then what Jack did to solve this was they changed the loop count, right, the trip count, to have some cache blocking. And when he did this, he basically reduced the trip count. Then he's able to get the performance about equal on the Haswell and the Knight's Corner. But what I want to note is this is not necessarily a portable change, right? I mean, do you really want to go through your code and make your loop trip counts match up with the cache hierarchy of a particular architecture? I mean, I think that's going to be a real challenge for application developers. And so I bring this up as a caution to some of the portability discussions. So quickly, the lessons learned so far, I think the good news is there does seem to be some low-hanging fruit in vectorization. Maybe that means some of our codes aren't perfectly well written, but we are able to get some pretty fast gains quickly. Understanding if your code is memory bandwidth bound, CPU bound, latency bound, it's really important, but most people don't seem to really know where they are in the spectrum. And that's because it's kind of complicated, right? I mean, it can change from kernel to kernel, it can change from architecture to architecture. The optimization techniques are quite dependent on the algorithm and the code. So we can provide users, guidance, profile this, look at your memory bandwidth. But the recipe, what you'll actually do, will be very different depending on the different algorithms. Some people are looking at, network performance. Other people are putting in OpenMP. Some people are looking at memory locality. So all these 20 teams are not doing the same thing right now. And then finally, portability is a key concern. So hopefully we'll talk more about that. And that's all I have, except that we're hiring. So send us your postdocs. So thank you.